My name's Ousterhout, and today I hope to convince you why we should be thinking about software performance as a shape and not as a number. So first, just a little bit about me. I'm currently a software engineer at Lightstep, where I'm working on building tools that help developers understand the performance of complex distributed systems. These are currently mostly focused around distributed tracing. In my past life, I got a PhD from UC Berkeley. My PhD dissertation focused on understanding performance of large-scale distributed systems, focusing specifically on large-scale data analytics frameworks like Apache Spark. I did some work on understanding Spark's performance today and found some surprising things that went against conventional wisdom around performance bottlenecks in Spark. And I also did some work thinking about how we could re-architect these large-scale systems to make it easier for users to understand performance. I'm also a committer and PMC member for Apache Spark, and my work on Spark has focused on optimizing performance of the scheduler and maintaining the core scheduler code. I think throughout all of these projects, the thing that has most interested me is thinking about how you can take these systems that are very complex and distill out the sort of simplest, most essential parts to help the people using them understand why they're behaving the way that they are. So in this talk, I'll be talking about performance of distributed systems. I hope you walk away with this talk with a sense of some of the tools that you could use that would be most helpful to understanding how these systems behave. I'll start by talking about what's going on, how you can measure symptoms in your system, and I'll argue that percentiles are not enough, that you need to look at performance as a shape by using histograms to understand what's going on. Then I'll talk about the next step, looking at why behaviors are happening once you understand that they're there. And I'll argue that the biggest problem here is reducing the search space, that there's too much data right now, and the most important thing that you need to do is to reduce that data to find the parts that are most important. And then finally, I'll wrap up by talking about observability as a whole and how these earlier two parts of the talk drive a new scorecard when you're thinking about what's important for observability tools. So first, what's going on? I want to talk about what happens when developers want to understand the performance that's being provided by their system. This might be understanding the performance that's experienced by end users, or it might be understanding the performance of some internal system. Is this internal system providing the service level objectives that it's promised to the other services that depend on it? So I'll walk through a history of how folks have thought about this over the last decade or so. So back in 2002, folks were starting to run things on the cloud, and what a typical app might look like is that there was a monolith running on bare metal somewhere, and the way that we thought about performance was that we looked at average response latency over time. This graph looks kind of boring. The average is flat. You can barely see it. It's around a millisecond. Here, time is progressing from left to right, so now is on the right side. And using average response latency was based on a couple of assumptions. The first was that the latency was normally distributed, or something like that. And that was important because it meant that when you were looking at the average, you were essentially seeing the whole behavior of your system. You were assuming that the behavior was kind of clustered around this one number, and if there was some problem, you would see the average moving, and that would be reflected on this graph that shows you the average. Now, by about 10 years later, in 2012, the landscape had changed. And now what applications typically looked like was a monolith, but that was talking to a bunch of managed services that it depends on. So here, my monolith is that big gray box, and it's talking to a bunch of other services that fan out to a bunch of servers. Those ones highlighted in yellow are the ones that need to respond to fulfill my request. Now, if you start thinking about why average latency doesn't work anymore, you can ask yourself what the response time for this service is going to be. It may be tempting to think, well, it's just the average of all of the components. But if you think about this for a minute, you'll see that the response time is actually going to be the worst case for any of these components. Typically, your service can't respond until the slowest thing that it depends on is finished. So as a result, the tail response time of these sub-services becomes a lot more important. Just to belabor this point for a minute, if you imagine that each one of these servers that you're depending on has 1 millisecond average latency, so it's usually pretty fast, but it has 1 second 99th percentile latency. So 1% of the time, it takes a second or more to respond. Back when you just used maybe one of these services, this latency distribution is exactly what your service would provide. 1% of the requests would take more than a second, which feels like maybe it's okay. On the other hand, if you use 100 of these services, then suddenly that tail response time for the things you depend on is the thing that drives the performance of your end service. If you use 100 of them, 63% of the requests will take greater than or equal to a second. For that reason, people started caring a lot more about tail response time. They would typically measure something like 99th percentile response latency. Here along the bottom, there's a time series for that same service that I showed earlier, where the average was that kind of boring flat line you could barely see. And now when we're looking at the 99th percentile response latency, you can see a lot more is going on. Now, there are still a bunch of assumptions underlying this number. Essentially, we're still assuming that the latency distribution has a single behavior, that there's this one kind of bump if you look at the histogram, and that when we're looking at the 99th percentile, we're seeing one side of that, so now we're caring about the tail performance more, but you're still making this assumption that you're kind of seeing the whole behavior of your system by just looking at a single number. Now, fast forward a couple more years now, we're in 2018, and what applications typically look like is there's probably still some monolith somewhere that has a bunch of the functionality, but it's relying on an increasingly large number of microservices to do its job. And the reason why this changes the way we think about performance is because there are now a lot more behaviors that can happen in your system. Going back to that assumption that the latency distribution has one behavior, that's very rarely the case when you have all of these services that are acting together to serve requests. So here are a couple of examples of the latency histograms of various parts of our internal system of microservices. We didn't pick these distributions to look weird. This was sort of a random sampling we took of a bunch of our internal services. We were actually looking to see if we could find any that looked normal. And you can see that none of these services really look like anything close to normal. Just a reminder of what you're looking at when you're looking at a histogram. Along the x-axis is latency, so faster is on the left side, that's good. Slower is on the right side, that's bad. And then the y-axis here is count, so how many things happened. I think it's always important to remember this because we're also accustomed to looking at time series graphs, where usually higher is bad, but when you're looking at a histogram, remember that things further to the right are bad. So this bottom left histogram, performance actually seems okay. Most of the stuff is pretty fast, around 100 microseconds. I know it's hard to see the axes out there. But then these other histograms, you're seeing much more varied behavior. Like the top left one has these kind of two clusters of behavior. One group of requests is really fast at a couple of microseconds, and then there's this other group that's taking a couple of seconds. And if you tried to characterize that top left histogram by any one number, you can start to see pretty quickly why it wouldn't be very representative of what's actually happening. Like if you looked at the median or the average, you might end up with some number that's in between those two modes of behavior that actually isn't describing what any of the requests in your system are actually seeing. So to talk about another example of this, this is a problem that I'll return to throughout this talk, where I was trying to debug some user-reported issues where we were hearing that one of the pages on our software was loading too slowly. So here, what you can see is the median latency was fast. It was around 500 milliseconds. It's hard to see that line along the bottom there, but it wasn't moving much. But there were a couple of these cases where the 99th percentile was really slow. Like this one circled time, the 99th percentile was taking 17.7 seconds. But here, at this point, when I was on call, it was hard for me to understand how bad of a problem this was. Like, what was actually happening between these percentiles, and how worried should I be about how bad the performance is? If I look at the latency histogram with what's going on, it was a lot clearer to see. Just as a reminder, the latency is along the x-axis, so slower is to the right. And what I can see now is that there are these sort of distinct clusters of behavior. There's some requests that are being served very quickly. There's a big cluster that's around a few hundred milliseconds, so those ones are fine. Those are still fast enough. But there are these two slower clusters around a couple of seconds and a couple of tens of seconds, and those really are a problem and are things that I should look into. And you can get much more here from looking at the histogram than you could get by just looking at that time series. So with current systems, these high-fidelity latency histograms are important to measure because they reveal these distinct performance behaviors. Now, it might be tempting to think, there's a bunch of different behaviors. Can we just use more time series? Like, could we use a bunch of different time series graphs for each of the possible behaviors that could be happening? And the problem is here, if you have this very unscientific graph looking at the number of microservices and the way those sort of combine into a number of behaviors, the number of distinct behaviors grows combinatorially with the number of different microservices that you have. If you think about sort of a network of microservices, there's a different behavior for each service that's talking to each other service, depending on how slow each service is, and it's very difficult to capture these all with individual time series. Whereas if you look at a histogram, you can very clearly see these sort of distinct clusters of behavior that describe your system. So today, the thing that is important to measure is to measure these high-fidelity latency histograms. Now, one tricky part about visualizing histograms that I'll just talk about briefly is it's non-trivial to think about how to visualize a histogram over time. When we wanted to look at a percentile over time, we look at a normal time series graph, and time is along the x-axis. But you may have noticed that when we started to look at the histogram, we lost the dimension of time. Now we're just looking at a snapshot of what was happening at a particular instance. So there's some cool examples of how folks have visualized these histograms over time. This is something called a joy plot, where here you've graphed the histogram a bunch of times, distinctly sort of separated by the y-axis. So here time is moving along the y-axis, and you have this kind of 3D representation of the histograms. And so this left one in black is one that we did for a latency distribution in our own system, where you can see some changes happening over time, where there seem to be more outliers earlier, and we're losing some of those outliers. But I think for folks who are interested in observability or in visualization, this is sort of an interesting question that's not totally solved, is if you want to look at a histogram over time, what is the most effective way of doing that? And is kind of stacking them up like this showing you enough data? The one on the right is sort of a cool example looking at global warming over time, and you can see how the histograms of temperatures wiggle around a bunch, but there's a clear movement to the right. So to return to this question of what's happening in my system, hopefully I've convinced you that averages are less useful than percentiles, and percentiles are much less useful than latency histograms. There are a couple of other things about measuring today's systems that makes doing so complicated. So another issue is that you need to measure different dimensions. There's typically some variability in the data, and the only way to understand that variability is by breaking the data down into the different dimensions that explain that. So as one example, here's one graph of some metric over time. Let's say that it's latency. And in this case, the metric is completely described by the machine that the particular system was running on. So here, once I've split the data by machine, you can see that there's this one machine that describes all of the variability in the graph. Now, there's this word that has sort of come into vogue in the last couple of years, which is cardinality. What this word means is just the number of different values for one dimension. So here, what makes this measurement difficult is that sometimes these dimensions become things that have very high cardinality, where there's a lot of different values. And in order to understand your system, you need to break up the data to see how each of these values performs differently. So this was one example talking about machine ID, where the cardinality was the number of machines in the system. This one may seem more doable. Like, there are some number of machines, and it's probably reasonable to have metrics per machine. But if you think about some other important ways to split your data, it becomes clear that the sheer number of values is hard for metric systems to handle. Usually once cardinality gets into the sort of hundreds, it's hard to track these metrics separately. So another common one that's frequently very useful is user ID. And here the cardinality is the number of users in the system, which you can imagine quickly becomes pretty large, but is often a very important way of describing your data. So this is another example from our internal system, where there's this call, update span group statistics, that's kind of critical to ingesting the data for our system. And here the latency histogram is showing me that there's a couple of different behaviors going on. There's some that are very fast, and then there's a bunch that are quite a bit slower. And in this case, I can describe a lot of the variability in the data if I just separate it by customer. Here, I've added a search term for a particular big customer whose name I've redacted, and you can see that this big customer has calls that are consistently slower. And then if you look at some of our smaller customers, their calls are typically faster. So this has helped me to understand what's going on, and in this case, to understand how important this problem is. If the bad behavior is mostly happening for our big customers, it's probably the ones that we care about more, and therefore worth looking into. So the problem with cardinality is some of these values are really useful, but some of the values with high cardinality are not very useful. Like, one common example that we see in our customers' data is that they'll have some tag for the deadline of a request. So that tag will be something like the number of milliseconds in epoch time when the request expires. And if you start to think about the cardinality of this value, that's the number of unique milliseconds that have elapsed, which starts to become a pretty big number. But the problem is it's also not actually useful. Like, it's pretty rare that it's useful to group by each of these individual deadlines to see what the response time is. And the key challenge here is that it's pretty hard to convince developers to only add tags that are useful. Someone probably finds this deadline useful for something, but it's hard to restrict the way that folks use these metric systems to keep them from adding these things. So it's crucial that the metric systems can handle these high cardinality tags, even in cases where they may not be particularly useful, but where they still have very high cardinality. It's pretty hard to separate the ones that are useful from the ones that aren't. So to recap, I want to go through some of the things that are important for us to be able to measure the system. The first is the statistical precision. Now with the complexity of current systems, it's important to have a precise histogram rather than just a couple of numbers to try and summarize the data. The second is cardinality. If systems impose cardinality limits, it becomes much more difficult to understand how you can describe the variance in the data. Another thing that's important is the volume or sampling limits of the system. So here's an example where in our internal product, we decided to try reducing the number of histogram buckets from 200, which was the default, to 40, which we thought 40 different buckets seems like it should be enough to describe a lot of data. And what you can see is that you pretty quickly lose the usefulness of this histogram. What used to be this sort of distinct shapes now looks like kind of a blob and is no longer very useful. So it's important that the system can handle high volume and does so without doing too much sampling, without losing the fidelity of the data. Then there's two other dimensions that are important that people usually don't think about until they realize that their system doesn't have them, and then they feel sad. The first is freshness. How quickly does data appear? So if you look at a timeline where this is now, your system almost never provides data right up until now. There's some gap between the current time and the data that you can view in the metric system. And if you read some of the old Google work about, they had this paper called Dapper about distributed tracing. And one problem with Dapper was that they used a bunch of analytics tools to analyze the data afterwards. And while that data was really useful, a lot of it wasn't available until sort of hours after things had happened, which really limited the usefulness of those tools for debugging and firefighting situations. What we found is that this freshness often needs to be on the order of sort of tens of seconds for it to be useful when people are trying to use it to debug an outage. And then the other important time dimension is the horizon. How long is the data kept for? It's usually useful to have a few days or maybe a few weeks of data. It's pretty rare that anyone cares about data that happened a couple of months or a couple of years ago. So if you just take a step back and look at all of these properties, I think the important thing to see here is that when you're doing measurement, what you really want is more data. You want this data with high fidelity. You don't want it to be too heavily sampled. You want to be able to look at all of the different dimensions of the data, even when it has high cardinality, and you want it faster and for a longer horizon. So that was about what's going on. Now let's shift to talking about why it's happening. And in thinking about this, I think we'll see the sort of opposite trend, that looking at what's going on, it was interesting to see as much data as possible, but to understand why it's happening, what we actually want is a system that helps us reduce the data to see only the things that are useful. So to go back to that example of why is the page load slow, what I was able to identify before is that there were a couple of different clusters of behavior, but what I don't know yet is why those things are actually occurring. So let me walk through a sort of typical debugging workflow that I'm guessing sounds familiar to many folks in the audience. This is certainly something that I've done before and that we hear from a lot of our customers who are using various metrics tools. So typically what happens is folks first look at some metrics. Maybe they got a page because some metric is too high, or maybe they were just looking at some dashboard to understand the performance of the system, and they've identified that something is wrong. And then they go and spot check some logs or traces. And then for the most important part of this workflow, the sort of prayer, where they hope that they find the right log or the right trace that will give them this kind of aha moment that tells them what was going on with all of those slow requests. So to talk about an example of this, again, this is that one slow page load. And sometimes those moments of prayers kind of don't pan out and you get stuck. And then the thing about engineers is they're really great at coming up with explanations of things. So you start to hear explanations that sound like this. This is my favorite one that I hear a lot. It was a networking blip. This seems to be the convenient explanation for almost any problem, is that something went wrong in the network, and it probably won't happen again. Or maybe there was some garbage collection. Or then they get increasingly vague, like it was probably just a one-time thing. And usually no one actually says this, but if you take a step back, these explanations often start to sound like something magic happened. Like there's no way we could have predicted it. It probably won't happen again. We probably can't do anything to prevent it happening again. So let's sort of pretend like it never happened. And I think if there's one thing that you take away from this talk, it should be to keep an ear out for when you hear these explanations that sound like magic, or when you're coming up with them yourself, and think about that's usually a sign that you don't have the tools that you need to understand what's going on in your system. And what I hope to also convince you of is that a lot of times these things that look like magic are actually a really important behavior that's an indicator of some future problem, or maybe that's actually making all of the performance worse, and it's just particularly exacerbated in this one case, and these things are often worth actually solving. It can also be tempting to think, like, maybe I could have solved this problem if I only had more metrics. And I think there's two problems with this. The first is that these graphs often end up with a lot of correlation. Like, this was for a particular outage in our system where you can see there was something that weird happened in all of these graphs, but they don't tell you about causation. And so what this often results in is a scenario where somewhere between 0 and 1 person in your organization can look at these set of metrics and tell you what the root cause was, and everyone else ends up being sort of stumped. The other problem is that it can exacerbate the temptation to think about things as magic. Sometimes you'll have one metric for each root cause, and it can be tempting to think like, oh, a bunch of smart people thought about the potential causes for this problem, and it doesn't look like any of them did actually cause this, so therefore it's probably some cause that I don't actually care about. So I think the takeaway here is that more what is not the same thing as why. And in fact, answering why often involves getting less what and sort of honing in on exactly what the problem was. So the key challenge in answering this why tends to be reducing the search space. So let me walk through how I did that for this example again of the slow page load. So I think one common trend when people are thinking about debugging is that the debugging process is very iterative. Typically, you start off with some set of questions or some set of kind of hypotheses that go about what might have gone wrong. And the debugging process is essentially a hypothesis testing project of walking through each of these hypotheses to decide whether or not they're correct. So I'll walk through some of mine. You'll see some of them were right and some of them weren't. So my first guess was maybe this slowness was happening due to some errors in our system. I knew that sometimes there were certain errors that would occur and that they might limit the system's throughput. So in this case, what I did is I looked up the latency histogram for the service that was causing the problem, and I looked for just the cases where there were errors. And it's starting to look like there's actually a bunch of errors that were happening. And so I started to suspect that this might be the problem. And in this case, the thing that helped me decide whether my hypothesis was correct or not was getting sufficient context. Here, what I did is I enabled a bunch of context about what that histogram looked like at various times in the past, looking at it from an hour ago, a day ago, and a week ago. And in this case, what I could see is that these errors were actually normal. They've been occurring for a while. And this sort of thing is really useful because if you have a system with even sort of a little bit of complexity, there are typically kind of infinite many behaviors that look weird. There's a bunch of weird stuff going on at any given time, and you can't fix all of the things that look weird when you're trying to debug a problem. So it's really important to rule out the things that look weird but actually are normal and are not the cause of the thing that you're looking at. So here, the historical context helped me realize the slowness was definitely not due to errors because these errors are old. So the next thing I started asking is, okay, I have this example of something that took 17 seconds. Can I look at that one example and understand what about it took so long? So let me take a brief diversion to talk about what distributed tracing is. Lita gave a great talk about this earlier today that you can watch later if you're interested in a more detailed explanation. But in brief, what distributed tracing is if you don't know what distributed tracing is, you're probably familiar with logs, where most of the servers in your system have some logs. And the basic idea of distributed tracing is to take all of the information about a particular transaction, so it probably is sprinkled in a bunch of the logs through a bunch of the servers and tie them all together. So to trace everything that's involved in serving a particular request. So distributed tracing will build this tree of what happened in serving the requests and tie all of those things together, both with some metadata about what happened and also with some timing information about what happened. So let's look at a trace from that one example where things took 17 seconds. Here what you're looking at in the trace is the time is progressing from left to right. Then this thing in the middle is showing me the different services that were traversed as part of this 17.7 second page load. So at the top, we started off in something called crouton, and then at the end, we ended up in this service called live view. Each one of the rows here is showing you a single operation where the width of the bar is the time taken. Now, the other thing that's really useful here and helpful for understanding the why is understanding the critical path. there's typically a lot of things that are happening in parallel. It can be tempting to just look for the things that took the longest, but the only things that are important are the things that are actually on the critical path. So here the yellow bar is showing me the critical path, and it's showing me that it's blocked on listing objects. And here what's important is it's helped me rule something out. I think I probably would have guessed beforehand that the thing that was slow was actually reading these objects in. That's happening below off the screen where it's scrolled off, but the important thing is that that's not on the critical path. The only thing on the critical path is listing the objects, which is the thing that's slow. So in this case, we optimized the time to list those objects and then redeployed the code. And here you can see time has advanced a little bit. There's that 17.7 second one in the middle. And I can see that latency has improved a little bit, but it still hasn't improved enough. So I need to do some other things to improve the performance. So the next thing that I wanted to do was to hone in on this one part of the histogram where the results were slow. And again, this is where the histogram can be very helpful because you can hone in on just that one mode of behavior that you actually care about. Now here, what I'd ideally like to see is some idea of correlation. Can my tool tell me what aspects of these things that were slow is correlated with the fact that they were slow? Like, what's different about them than the rest of the operations? Unfortunately, this was using Lightstep, which is the tool we've built, which doesn't do this yet. I actually don't know of any tools that do this. So the way that I tend to do this is by hand. So I clicked on a bunch of the examples from in this histogram and a bunch from out of them to try and understand what's different. And in this case, what I figured out was distinct about these requests that were slow is that they were coming from some important customer. That one of our customers was reading a lot more data, and that's why the page load for that customer ended up being a lot more important. And what you can see here is that that thing that I was really tempted to explain away as just magic or a networking blip earlier, it's true that it wasn't something that happened hugely often, but it was something that was happening for one of our biggest and most important customers, and so it actually is very important to solve. And furthermore, it was a leading indicator of more problems. This was one of our customers that has the most data, so if we had ignored this problem, it's something that more and more customers would have experienced over time as they send more data into our system. So figuring out the source of this sort of magic issue ends up being really important. So zooming in on the critical path to understand what's going on in this slow example, here, what I can see now is that the thing that's slow, it's probably hard to see on the left side here, but what each of these things are doing is they're decompressing and unmarshalling the data. So what's slow is just deserializing the data that it's read into some internal data structure that we can use. So here, the question that I would start asking is contention. There's some shared resource, the CPU, that in this case the request is bottlenecking on, and what's competing for this shared resource? Is it actually just this one customer's request that's important, or is it the case that there are a bunch of requests happening at the same time and they're all competing, or is this one request using too much parallelism? There's a talk from Strange Loop last year from our CTO Spoons that goes into a lot more depth on sort of visualization tools that you can understand this contention. But again, the sort of trend here is that there's something slow, and I want to hone in on what exactly is the root cause of it, like what is contending for this shared resource. So to recap the different things that we did to answer why, the first thing that was important was, again, this freshness and horizon. Like, how quickly can I get the data about what's going on to analyze it, and then how far back does it go? It was useful to get data that went sort of a day or a week or a month back so I could compare it to see if it was normal. Then all of the other things on this scorecard you'll notice are things about reducing the data. So one thing that was helpful was context, looking at historical context to understand if it was normal. Another thing that's really useful is looking at value context, like if you see a value for a particular tag or attribute of the data that looks weird, can you get some context to understand whether that was different than other normal requests? A third thing that was important is the critical path, helping us rule out a bunch of things that happened in parallel but didn't actually matter to the response time of the request. We also talked about correlation, trying to separate out which of the features of the particular things that are slow are unique to those operations, and doing this sort of just in time. Like, my system couldn't necessarily predict in advance which requests I wanted to correlate to see that they are different, so can it allow me to do this sort of just in time analysis? And then also contention, thinking about what's responsible for the use of a shared resource and how can I use that to speed things up. A final why that I didn't talk about much is error provenance. You'll often see a scenario where there's some error, and it's important to understand which upstream service it was talking to. This was something that Lita talked about a little bit in her talk this morning, and that looking at a distributed trace can be really helpful for doing. When you have some error, for example, in front-end user requests, and you don't understand which of the services involved in that request caused the error. So just to recap this why, you'll notice that pretty much all of these things are about reducing the data. The thing that was helpful was not getting more data, but understanding which of the data was actually important. So with this context, I want to take a step back and think about observability as a whole, and what's the scorecard we should think about when evaluating different observability tools. So this is the classic sort of scorecard that I think folks think about when they're thinking about how to understand their system. They think of these sort of 3 checkboxes: metrics, logs, and distributed tracing. And the mentality is often something like, Google and Facebook understand what's going on with their microservice architectures, and they use metrics and logs and distributed tracing. So if we use these 3 things, we can understand our data too. But I think if you talk to folks who have all of these things, many of them will still tell you that they have no idea what's going on with their systems, or that they struggle to debug important problems. If you think about each of these things are really just data. And I think the thing that's more important to understanding the system is thinking about the actions that you do with that data, which is really just 2 things. The first is measuring systems, where you want a lot more data, and the second is answering why to understand those systems, which is about reducing the search space. And we talked about a sort of checklist earlier in this talk for each of these things, that at a high level for measuring symptoms, you want more data, and that these high-fidelity latency histograms are really useful for grouping different behaviors. And then for answering why, the thing you want to do is reduce the search space by having tools that allow you to eliminate a bunch of potential hypotheses about things that might have gone wrong. So to recap this talk, I think the first and most important takeaway is that there's never any magic in your system, only the absence of good tools. And if you think that there's magic in your system, it's probably because your tools aren't good enough. The second is that logging, metrics, and tracing aren't enough to understand your data. You need new kinds of tools to help you understand performance that will give you good measurement, latency histograms, for example, and that will also allow you to do refinement so you can reduce the search space of why. Building these tools is hard, and I think an interesting problem. If you're interested in working on that, come talk to me more. And with that, I'm happy to take any questions, and also feel free to email me if you have questions offline.